it's time to start. And I'm very happy to welcome everyone into the today's live tutorial presented us by the ALPAO, one of our Optica corporate members that is working on the development of adaptive optics. And I'm also very happy to host this seminar today, this webinar, because today, the 16th of May, is also the International Day of Light. It's every year this event takes place, and in celebration of this commemorable day, quite a few events are taking place around the world. So thank you very much for everyone who joined us for the webinar, that you have joined us today. And we're going to celebrate this day and this event together with actually having a presentation from the two very well-known researchers that are looking for the most distant lights at the universe. Today's topic of the theme of the webinar is the hardware and software solutions for real-time corrections of atmospheric turbulences in astronomical and also possibly Earth observations. And I'm very proud to present two of our notable speakers, is Dr. Olivier GUYON, a very well known astronomer from the Subaru telescope, and also I think a professor, right, Olivier, from the University of Arizona, and David BARR, the RTC engineer from the Durham University. So we have two speakers that are brought to us today by the ALPAO. And the webinar, for those of you who are with us for the first time, the webinar will continue as follows. We have our two speakers presenting about the theme of the event for approximately half an hour to maybe 40 minutes. And after this, we will ask the questions that are coming from the public. How can you answer the questions? You see in your window, there is a Q&A box. Please, all the questions that are related to the talk, just type down into the Q&A box, and after the presentations, we will read them out loud, and give our speakers opportunity to answer. And with this, I would like to welcome everyone once again and give the floor to the Olivier GUYON from the Subaru telescope, and also the professor at the University of Arizona, to introduce us to the topic of the real-time corrections for the atmospheric turbulences. Olivier, the floor and the attention of the public is yours.
Thank you, and thank you for providing me this opportunity to tell you about the technology and the wonderful things that are happening in adaptive optics. And I'll talk especially about the application side of these technologies. My area of expertise is exoplanet imaging, so I'll be talking about adaptive optics in that context. So I'll start with explaining what are the goals of adaptive optics system, specifically in this context. And then David will follow with some more technical description of how to achieve these goals. So this is a picture of the Subaru telescope where I work, where we have a so-called extreme adaptive optics system. And extreme adaptive optics is what is referring to the imaging of exoplanets with adaptive optics and large ground-based telescopes, which is extremely demanding. And so this is really one of the area of adaptive optics that is pushing technology. So what are the key steps to an adaptive optics system that is especially designed to take such images? So light from the telescope travels through the atmosphere without correction. The image looks quite bad. We have an image that's about 1 arcsecond of angle in effective size. With conventional adaptive optics, we concentrate this to the diffraction limit of the telescope, which is approximately 50 to 100 times smaller, depending on the wavelength and the site. These images are real images taken on the telescope with the system I work on at the Subaru telescope. We can have, in extreme adaptive optics, we have another layer of fine correction to get even better adaptive optics correction. And then we have instrumentation astronomical instrumentation. In the context of adaptive optics, this is designed to allow for imaging faint sources next to bright stars. This is the extreme adaptive optic application that involves blocking the light from the star and then directing it to an imaging camera, very often a spectral imaging camera. So here I'm showing real on-sky data where the data cube is scanning in wavelength. The exact backend instrumentation depends on the science application for the adaptive optic system. A little bit of context and history about what specifically I'm working on extreme adaptive optics. There are a few extreme adaptive optic systems in the world. I'm involved with two of them. The one is Subaru telescope, which I lead, and also the MAGEO-X on the Magellan telescope in Chile. These two systems are a little bit unique because in addition to being optimized for high contrast imaging, they're also research and development platforms, which gives me the opportunity to work with new technologies, test them on sky, validate them. So and this is of critical importance in this field. In terms of our the way we work, we developed our own real-time control system in-house, built around an open source platform that we developed and maintain. We adopt new technologies, new deformable mirrors, low noise fast sensor for wavefront sensing, and also advanced optics to block starlight and take it and implement our instrument that optimized for imaging exoplanets. We use off-the-shelf conventional commercial computer hardware to perform the high-speed computation and the high-performance computing. We use a mix of CPU and GPU platforms. So as I mentioned, these systems are optimized to image faint sources around bright stars, which can usually is planets or disks. So here are a few example images. On the left, image of a disk around a nearby star. In the middle, image of a well-known planetary system where the three planets are quite well visible. Sometimes we image other types of sources. I have Neptune in the top right of this screen, and interesting double star Capella, one of the bright stars in the sky, in the bottom left, where the two stars orbit in about 100 days from each other. So what is interesting about Extreme AO is it's the type of adaptive optics that's really pushing the performance into the extreme level of correction. So we have systems that are adopting the latest technologies in deformable mirrors and also wavefront sensors, cameras, and compute hardware. Typically, we run systems to about 2,000 actuators at speeds that can go up to about 3 kilohertz. The goal of an extreme adaptive optics system is not merely to achieve the diffraction limit of the telescope, but it's in addition to that to move as much of the starlight as possible away from the region where we look for planets and disks. So this is nicely shown in this example on sky images. In the near infrared, in the left image, we can see what we call this dark hole. The adaptive optics system is essentially digging this area in the image where which is dark, where there is very little starlight. Most of the starlight has been blocked by the coronagraph, so we don't see it. That's what's in the center of this square. We have 4 spots, which are calibration spots that we add to calibrate the image, to center it and understand the flux scaling. And on the right here, we have corresponding images in visible light. So even in visible light, these systems, thanks to their high number of actuators and high speed, they achieve the diffraction limit, and they also can do high contrast imaging. You can see the dark hole in the visible, this circle within which there is very little light left from the star. So just like any adaptive optic system, the real-time part of the system is this loop that takes the wavefront sensor measurement and convert it into a deformable mirror command. And so the simplest sort of block diagram of any adaptive optic system is one where light comes from the telescope, goes through the deformable mirror, which is the correcting element. So light is shown in the green arrow here. Some of the light is split, goes into the wavefront sensor to measure wavefront aberration. Computer, the real-time computer, uh, computes the command to correct for the wavefront error, and this runs in a high-speed loop. In extreme adaptive optics, we usually add a chronograph, some optics that are designed to block starlight. This loop, as I mentioned, needs to run very fast and there are a lot of actuators and sensors involved. So the compute requirements are quite significant. But by using real-time operating system, a mix of CPU and GPU hardware, we can close this loop at in our system. We can go up to 3.5 kilohertz and controlling about 2,000 modes with excellent timing characteristics. So here are some timing diagrams showing that the whole computation is done on the order of 300 microseconds with timing jitters that are on the order of a few microseconds. So excellent timing, stability, and speed are combined. In extreme adaptive optics and more broadly in extreme adaptive optics, there are new technologies and that open up very exciting opportunities. We have low noise, high speed sensors, imaging sensors that are constantly improving, allowing for faster wavefront sensing, more capable wavefront sensing with multiple wavefront sensors. We have more deformable mirrors with better precision, speed, and number of actuators, which allows for better correction. Some of it can also be done by in multiple stages with a woofer tweeter architecture. We of course have high performance computing hardware and software that is coming online, and advances in optics, especially astrophotonics, which I'll describe in a couple of slides. So these opportunities really change the way we're thinking about adaptive optics system in the future. In the context of extreme adaptive optics, one of the big change that is happening is the science camera is becoming integral part of the adaptive optics system itself. So we no longer have this single wavefront sensor that is measuring the wavefront. The science camera after the chronograph, which can be a high-speed camera, is participating in the process of correcting the wavefront and also measuring and calibrating it. This involves speckle control, shown on the left here, where using the focal plane, we can dig an area, iteratively dig an area that is dark. We can do PSF reconstruction using the wavefront sensor telemetry, shown on the top right here, leveraging new machine learning frameworks. And we can also use the backend focal plane image to constantly improve the adaptive optics correction, learning from looking at the result of the adaptive optics system running. Another big evolution that is starting to happen is advances in optics, especially integrated photonic circuit, where we can combine the functions of wavefront control, removing the starlight, and interferometric calibration and spectroscopy in an integrated device that are highly stable and optimized specifically for the purpose of the adaptive optics system. And so this is an example of the old distinction between what is a wavefront sensor and what is a science camera sort of becoming more blurry, where the same optics can participate into both. So what are we looking at in terms of the needs for high performance computing and real-time computing, given this hardware evolution is a much more capable picture for what an adaptive optics system is, and especially here, as shown in the red box, what part of the system need to run in a real-time high performance computation. So not only we have the closing the loop using wavefront sensor signals to issue commands to the DM, but we have systems that are able to calibrate themselves on sky. We have a big need to collect telemetry from multiple wavefront sensors and perform more advanced wavefront control, including predictive control, and sensor fusion, merging the information from multiple waveform sensor for an uh, improved correction, and also PSF reconstruction is becoming quite important, where we can take all of this information and reconstruct where is the starlight in the science image, which is fundamentally important, especially in the extreme adaptive optics, where our main noise is the starlight that is left. So in terms of lesson learned from a user point of view for the software part of it, and especially the real-time control part of it, the data format and how they enable modularity is absolutely essential to our needs. So we iteratively converge to having a data format which is a shared memory. We call it a stream, which embeds also timing information, so that instead of thinking of an adaptive optic system as a main control loop with a start and an end, it becomes a chain of compute units, each acting on some of these streams. And we can implement, with this flexibility, this modularity, we can implement and grow much more capable systems, much more aligned with where the technology is leading us. Another lesson learned is that accurate and stable timing is critical to a lot of the functions of these more advanced adaptive optic systems. So we understood fairly on that we needed to measure the timing characteristics of a system very accurately. We also needed to ensure that they are stable, which is a technical challenge when the system grows in complexity and also spans multiple computers that need to be synchronized. But this is important because a lot of the advanced tools, for example, predictive control, merging signals from multiple waveform sensor, this really requires understanding the timing very accurately. And I think our field is also moving into better understanding of this timing, of the timing characteristics of the hardware. For example, deformable mirror doesn't move instantaneously, and leveraging this for better control. So as a conclusion and giving some perspective, the advances in hardware, detectors, optic deformable mirrors, are really enabling much larger scale adaptive optics, but also ones with much more advanced capabilities. So this is very exciting for all of adaptive optics, and also for the field that I work on, the extreme adaptive optics. The science instrumentation is becoming an integral part of an AO system. So the old traditional distinction between what is an adaptive optics system and what is an instrument is becoming a little bit blurry, especially we see this in extreme adaptive optics. AO systems are becoming much more capable by integrating multiple waveform sensor and implementing these advanced AO control schemes. And finally, in the context of extreme adaptive optic system, all of this is pointing to a very exciting and bright future, where using the next generation of large 30 to 40 meter ground-based telescope, we are heading towards being able to image habitable planets or a nearby star, which is extremely exciting scientifically. So this is my last slide. I'll hand it over to David for a more technical description of real-time control.
Thank you very much, Olivier. And then let's hear the continuation from David BARR, RTC engineer from Durham University.
One moment. Okay, so thank you very much for that great talk, Olivier. So yeah, as Olivier said, I'm going to go a bit more into some of the technical aspects of the RTC. So yeah, so what I want to really talk about today is just talk about some of the compute hardware that Olivier was talking about. So a lot about like GPUs, CPUs, and the main software pipeline that builds up the RTC, and some of the current work I'm doing here at Durham University on DAO and Harmony. So the first thing I really want to talk about in the RTC is yeah, what is the RTC? So this is what Olivier was explaining. It is what takes the wavefront sense pixels and converts them to the commands used by the deformal mirror or any other correcting optics you use. But one of the big things that gets missed out in a lot of these talks is the RTC is not just this pipeline from pixels to DMs. It includes a lot of supervisory functions, optimizations, logins, alarms, and controls. And a lot of the time that this gets forgotten about. But in talking about hardware, I want to talk about a problem that has plagued my career for the last, 10 years or so. So 10 years ago, 12 years ago, I started my PhD on looking at what is how can we reduce the adaptive optics latency using many core processors. And this was in the domain of looking at the new 40-meter class telescopes and saying what is possible with today's commercial off-the-shelf technologies and how can we apply this to 40-meter class telescopes, and is it actually possible? So during that time, it's a bit of a story, but I'll try and keep it as quick as possible before we get on to some other technical aspects. I looked at two very novel technologies at the time. So the Xeon Phi, which I actually have one sitting here, which is a very GPU-like system, but just using x86 instruction set cores with GDR5 memory. So it was great for accelerating memory-bound problems. And the Tile GX, it was a network card with lots of ARM processors on it. Great for optimizing network traffic. A lot of cameras now using Ethernet for transporting camera data. So these two technologies looked really promising. So I spent 4 years of my life looking into them, testing them, setting up systems. And then before I even submitted my thesis, they both were discontinued. Anyway, which became a little bit of a theme of my career so far. So after that, I went to work for ESO, and my main job was in the RTC group. We're looking at Sparta. Sparta is ESO's standard platform for adaptive optics real-time applications. And it was first used on SAXO for Sphere. SAXO is the RTC for Sphere. Sphere was an extreme area system for the VLTs. And so this design work started back in the early 2000s. The earliest I can find evidence from and papers from was about 2005-ish. Very low latencies. So we're talking 90 microseconds latencies going from your last pixel to last command. This was built on very specific hardware of DSPs, FPGAs, but with a CPU cluster for supervisory tasks and optimizations. And so this has been running on the telescopes for the last 10 years or so, but started in the early 2000s. And my last job at ESO before I left was commissioning ERIS. So this is a system that went on Sky in 2022. And so if you're looking at hardware that was designed and built an RTC on in the early 2000s, and you're putting it on Sky for the for a new instrument going on Sky in 2022, almost 20 years later, not quite, but almost 20 years later, and expecting a lifetime of 10 to 15 years, that's a long, long time, and not something most people when building these systems think about. And so this is kind of one thing I wanted to impress. Obsolescence is a problem, and we need to think about it for these long-term things. So for this system in ERIS, and AOF, so it had News, Hawkeye as well, and Sphere. These boards, these FPGA boards we bought in the early 2000s, late 2000s, boards start failing. And we knew this. There was no decision to continue Sparta's lifespan and move it on to new hardware at this time. The idea was the lifetime of these instruments would be based on the lifetime of the hardware. So, and we bought a bunch of spares of these specific FPGA boards, and yeah, the lifetime was meant to be replace them as they failed with spares. And across all four instruments, you had 10 plus boards, but they started failing. So we replaced them with the spares. It was fine, but they started failing faster. And we realized very quickly that not only were they failing faster, if something wasn't done, we'd lose some of these instruments, maybe all of these instruments on the VLTs, which was not an option. So we started a project to develop a replacement RTC based on CPUs, respecting all of Sparta's interfaces. So the whole of AOF, which is a 4 LGS system, is now done on a single AMD EPYC server, sub 200 microsecond latency, sub 1 microsecond jitter. It's now on Sky and working. But the thing I want to get out is you do need to think about the long-term and lifespan of systems while you're in the design phase. Yeah. Anyway, quick lesson learned from this we did was be careful how you log your errors. Cameras run fast in an RTC. They're probably one of the things that run the fastest, along with the DM. Between the DM and the RTC, they pick up errors first. And so when your RTC starts kicking up errors, even if you say RTC error, camera's not working, people just see RTC error and blame the RTC. So think about how you announce your errors, because otherwise you'll be blamed, and people don't like the person announcing the errors a lot. Anyway, so hardware selection these days. There's absolutely many different technologies you can use, but the main ones are CPU, GPU, DSPs, and that, depending on what you're doing, any of them can be great. So CPUs, they're cheap. Everyone's got experience programming them, but they can be complicated to tune, especially for low latency environments. GPUs, they're becoming far more common. You're getting more and more skilled programmers working on them, but I/O is still an issue. I know some teams have been looking at GPU Direct, which is a technology of bypassing the CPU entirely. And for them, the results I've seen looks brilliant. It does seem rather complicated, but I'm sure if you ask them, it's not. FPGAs, they're very difficult to program, time consuming, but you do get brilliant performance, low latency, low jitter. But considerations are probably, you need to look at raw performance. And this is something we all in the RTC community are guilty of. I know I am. We, especially at conferences and especially universities, we pride raw performance over everything. So every conference you go to, you see X microseconds, X microseconds jitter. And that's what everyone cares of. Normally, because this is where the publishing comes from, this is where you can get papers. But in the long term, it's not the only consideration. You need to look at who your team is made up of, what skill set do they have, who are the users, the lifetime of these projects, and the evolution of technologies over that lifespan, and especially cost. But I think that's all I'm going to really say on hardware. I know there's a lot more we can talk about, but I could just go on to what the RTC pipeline is in more depth. So the RTC pipeline is where you get your camera pixels readout into whatever compute unit you want. You calibrate that image some way, do some wavefront processing, get some slope data across this, across the wavefront. You do some reconstruction, so maybe some combining with other control paths. Then you do some control filtering, and then before you push it to your DM. And if we look at timings, so standard cameras, you look at readouts of, you integrate over time, and then you read out over another time before you can start your processing. So you're already 1 to 2 frames delayed of where your atmosphere was by the time you'll start processing those pixel images. So in RTCs, we like to pipeline this. So as soon as we get a few pixels in the RTC, we like to start processing them. And then we push that through a pipeline of computations before we transfer it to the DM as quickly as possible. And reducing this latency is really what our major aim on the hard real time is. So quick overview of camera readout technology. So there's a lot of them, but the main ones I've worked with, camera links. So there's GigaVision, so there's Ethernet, USBs, and coax express. And from an RTC's perspective, it doesn't really matter too much. you have to start working with whatever camera SDK you've got. But I'd like to highlight Aravis. So if you're working on cameras, Aravis is a great little open source project that takes GigiVision cameras and allows you to control any GigiVision camera using an open source SDK, so all of your camera controllers can look the same. It's what I use a lot. I really like it. And if you're using Camera Link, I highlight the Pleora iPod. It's quite a nice little box to convert Camera Link to GigiVision, so you can use your Aravis to control Camera Link cameras as well. I found it quite nice to use. Anyway, so calibration, I'm not going to spend too much time on this. I think everyone knows how you calibrate an image. So raw pixels minus your dark over your flat. This can be done standalone, or it can be integrated into your the rest of your wavefront processing unit for your slopes, which can be quite nice. I know Sparta worked like this, where you can touch a pixel once, and so you can leverage your cache coherence. So wavefront processing. Two major styles of wavefront sensors. We could talk about Shack-Hartmann's and pyramid wavefront sensors separately, but they're two different technologies to get your slope data or your wavefront data from an image. On the left, you got a Shack-Hartmann. This is a bit of a weird image I've shown. It's just I was working on the bench with Ali on this earlier, so I just got the images from him. It's a wide field one, so it's treated more like a solar AO image. And so the pyramid. Anyway, so Shack-Hartmann, you have a lenselet array in front of a detector. As each of the little lenslets focuses the light on the detector to create a spot, and from the deviation of a spot from the center of that wavelet, you can measure the local slope on that wavefront. So this is just showing a weighted center of gravity, but there's many other different algorithms you can use on top of that. Cross correlation, brightest pixel. Yeah. Pyramid wavefronts. I'm sorry, I think I'm going very fast over this. This is really just to give a very highlight of what's available. I'm not going into the science really behind it. Just what's available for the computing. The other one, actually, so go back to here. That's one interesting thing to say about this is you can start your wavefront processing as soon as the first sub-aperture of pixels have arrived on your in your computer. When, in contrast, the pyramid, you create 4 images on your detector from a pyramid, and you create your slope from the difference between the intensities in each of these images, pupil images. And so you can't start that calculation until half your detector's been read. So while we like to pipeline, you start the calculation much later on in the pipeline than you would with a Shack-Hartmann, but it does have many other important benefits. So the next step would be your wavefront reconstruction. In a typical RTC, the main reconstruction technique we use is matrix vector multiplication. We multiply our slopes against a command matrix to get a residual wavefront, and we do this with just a matrix vector multiplication. It's a memory bound, so it's the performance you get scales with the memory bandwidth of your system, not the number of cores you have. But there's other reconstruction techniques available. So I'm not going to talk very much about the control laws and filtering, but there's many different techniques like integrated PIDs, IRs. They have different benefits, but I'll move on from that quickly. So really the next thing to talk about is I want to talk about DAO and what I'm working on now. So about 2 years ago, I left ESO and I joined Durham University. And me and a guy called Sylvain Set, who used to work at Keck, and we were tasked with building the RTC for Harmony, which is a first light instrument for the ELT. So we took both our history, so mine working at ESO, his working at Keck, where he actually worked with Olivier a bit, and so inspired by his work on Cacao and especially the image stream IO. So at the end of Olivier's talk, he talked about stream and shared memory. So ImageStream.io is a library that allows inter-process communication via shared memory for images and other things. And so we've taken this and expand and work with it a lot, and hopefully we can give things back that we develop. Anyway, it's a great piece of technology. If you're building an RTC today, it's probably where I'd start. Anyway, so we took that, some lessons I learned over at ESO, and we're trying to build a new RTC that we have control over in Durham, mainly for Harmony. But our goal is that it can be used it's simple enough for AO scientists to use it, but powerful enough for the biggest telescope on the world to use it. So we've already interfaced with many standard hardware like the ALPAO mirrors or a lot of cameras. It's got distributed compute, telemetry, logging. It's CPU and GPU ready. And because it's backed by this Harmony project, it's going to have support for the next 10 years, which is great. So let's talk quickly about ImageStream.io. It is open source project that is for the streaming of the images. And so I've got an image of it here. So you've got one process on the left, which is connected to maybe a camera, maybe it's a formal mirror, maybe another compute process. That process will write into some sort of shared memory, and it has some synchronization tools, some metadata, and some timings attached. And so you write in triggers a semaphore, which can be read by another process. So from the example RTC pipeline I showed before, each of the separate processes can now be split between them using these shared memories. Which can be very, very useful, because then you can attach each process doesn't care what's on the other side of a shared memory. It could be a process reading from a fixed file, writing into shared memory, or coming from a camera, or whatever you want it to be. So out of box, we're offering pyramid wavefront sensing, Shack-Hartman, classical integrators, predictive control, lots of useful tools. And so we're starting to ramp up development on this. I'm going to move quickly on, so hopefully we'll release later this year, but we're having some problems with a UK export control law. Another thing I do want to highlight is a lot of people in the UK and Europe, we share a lot of code, we share a lot of code, software source, but we found recently, talking to the UK government, that certain parts of this can, under UK law, especially real-time control of the formal mirrors as part of AO systems, is restricted. And so our DAO has been rated this rating. I don't think you need to know what it means, but it basically means that if we share certain parts of our code base, we need to get signed end user certificates. But if you're interested in any of this, come talk to me later or send me a message. Happy to help out. But yeah, if you're building an RTC now, look at ImageStream.io. It is great. Quickly onto Harmony. So Harmony is a first light instrument for the ELT. It's a spectrograph. Yeah, there's a nice image of it. Not going to talk too much about what it is, but it's a big first light instrument for the European extremely large telescope. And so here we've been looking at building systems that, for a scale system, I'm just going to show some results, which has our reconstructor at 30K by about 5K. We spread it across 3 nodes. This is how our RTC looks from a shared memory and data processing pipeline, but we're getting low latency, about 250 microseconds, with tens of microseconds of jitter, which can be reduced even further with some network tuning. And so, okay, so on the left, you've got the chronogram of our system running, and on which predicts for our size system spread across our theoretical system, spread across 3-4 computers with a latency of 235. In reality, we're getting about 250. Anyway, just showing, hopefully it's been useful. I think I went very fast because I had a lot to cover. Not too confusing, but yeah, I think the two things are I want to point out at the end is think about the lifetime of your project when you're selecting hardware, and ImageStream.io is a really, really powerful tool to use. Thank
Thank you very much, David. Then the floor will be open for questions, and we already had quite some in the Q&A box. Olivier has answered a couple of them, so I will ask him then to comment some of them once again. And then maybe for some of the questions that are that also interested me, one of them was if this extreme adaptive focusing approach potentially applicable to laser light communications for either transmit or receive. Olivier, maybe you comment then live.
Yeah, that's a great question, and it's interesting that both application, Extreme AO and laser communication, they both are optimized for a bright source on axis, so they don't care about field of view, but they care about performance. So there's a lot of common technical solutions for both. I would say the main difference is that for laser communication, the amount of turbulence is usually larger. Um, because but that depends on the exact case, and also in Extreme AO we need to remove the starlight because that's our noise. For laser com, the bright source is usually the signal. So there are some common challenges, but also differences.
Okay, David, would you have a comment on this one?
No, I think he's answered it very well.
I actually am curious because laser light communication, it can be intra-satellites or then satellite to ground. And I believe in this respect, I'm curious to ask, how much of the additional equipment you need, because if it's satellite to satellite, you need to fly all this equipment up there. So is it rather satellite to satellite or ground links that you think will be most optimal to benefit from this technology?
Well, it's interesting. So satellite to ground, definitely very similar to ground-based Extreme AO looking at stars. Satellite to satellite, it all depends on, so there's no atmosphere in the way. It all depends on what are the optics doing, how stable are they. So what the first question would be an engineering question. If we can make the light very stable and the pointing stable, maybe actually we don't need much adaptive optics at all if we do satellite to satellite. Yeah.
Do you sense wavefronts polychromatically or single wavelength?
That's an excellent question because it is becoming a concern in our field. The adaptive optic system are becoming so good now that the wavelength dependency of the wavefront is becoming a limiting factor. So the traditional way to do adaptive optics historically has been we use the visible light for wavefront sensing, but our science is in the near infrared. And up to a few years ago, everyone assumed that's fine. We're measuring the same. We're measuring and correcting the same disturbance. It turns out that's due to chromaticity effect, that's not exactly the same, and we're starting to hit that limit. So a lot of I think this is mostly for Extreme AO. The other adaptive optics application don't really care about this. For Extreme AO, we're starting to pay attention to this. So the new systems have visible wavefront sensing to do most of the correction at high speed, but also infrared touch-up, because if we don't do the infrared wavefront sensing, we get these problems of the chromaticity of the wavefront itself.
Yeah. There is also new work being done into new detectors that can look at multi-wavelengths. So here in Durham, I know we've got a team working on MKIDs, which can do photon counting with specific with a wide band of different wavelengths, and we can get photons out with tagged with specific wavelengths. So it's definitely an area that people are looking for, as Olivier said, mainly for Extreme AO and planet finding. But yeah, it's definitely an area of work that's happening now.
Thank you. Then a couple of the unanswered questions. Could you please briefly introduce the nulling chip? Has such a device been utilized currently?
Oh, great question. So the nulling chip is essentially the equivalent of an electronic circuit, but with light. So instead of wires guiding electricity, we have waveguides guiding photons. And this is really a revolution in optics in general, but something that opens up exciting opportunities for adaptive optics, where we can program, we can write a chip that could do things that conventional optics could not do, and we can specify exactly what that is. We actually, there are a few groups working on this. At Subaru Telescope, we collaborate with a group in Australia that's making those chips. We test them on Sky, and we've been starting to use them. The main attract for us, the interest is that we can combine, we can do a nulling of the starlight, so we can do a destructive interference in the chip to remove starlight um, in a very clean way, and also combine wavefront sensing as part of the chip. So this is very exciting technology.
Mhm. But has such device been utilized currently?
Yes, there is an instrument which is called GLINT, GLINT. There are already a few science paper using this instrument that we've been putting it behind our Extreme AO system. And this is in very active development currently. So I encourage you to look at these papers to get a more technical details. But this is actually on Sky. We're using it and developing it in partnership with the teams that are building these photonic chips.
Excellent. David, any comment?
I've not worked with nulling chips before, so I'm going to leave it to Olivier to answer them.
Well, okay. Then another question comes: what causes DM vibration modes and how to calibrate it?
Maybe David, you want to take that one?
Yeah, sure. So I'm not 100% sure what you're asking here with DM vibration. But the vibrations you see in your system typically are from the system as a whole. Like you may have a chiller for your camera to get down to certain temperatures for the detector, and that will have a pump on it which vibrates the whole of your system. And you may want to try and compensate for this in some way. So there are some methods of doing this in the control filtering part of the AO system. Um, so there are some great papers out there from that. I think Canary were looking at it years ago with LQG control. I'm not going to go too much into it because the actual maths behind it, I don't understand. I've implemented them, but I would say look at the papers. They're much better than I could explain it.
Mm-hmm. But
And
it's not that they're. Sorry, Olivier, please continue.
I'll just add that when we build an extreme adaptive optics system, we usually the first thing we discover is not exoplanets but vibrations. All the vibrations that the telescope has.
Yeah.
But
Very yeah.
do you really calibrate for it, or rather you average and try to remove them by averaging?
It's all of the it's
Yeah.
all of the options we have. We are trying to identify them. We talk to the telescope, for example, people say, oh, we found this vibration. Do you know about it? Can you prove it? As David mentions, there are algorithms that we tune to try to notch this vibration. So the control, if we know there's a vibration, the control law of the adaptive optics can be
Mm-hmm.
optimized to take that into account, and also in the back end in the data processing. So it's
Mm-hmm.
we're there's no single solution. We're trying to push all of these solutions.
All
Yeah.
the buttons. Can the extreme adaptive optic approach be extended to precompensations for uplink? So this is again back to the laser light communication, I guess.
Yes, there are some teams looking at that. There is a team working with ESA at the moment. I think the project's called Alaska. They are looking at pre-compensation adaptive optics for laser communications with satellites, but that's about the limit of my knowledge of that. So maybe look at some publications by them. I don't know the exact details and issues they're having. I know a guy called David Jenkins is building the RTC over at, he works at ESO at the moment. But yeah, I don't know the current status, unfortunately. But I know that's what he's looking into. So it's definitely being tested.
Mm-hmm. Here comes another technical question also for the laser communication links. If we consider the use of adaptive optics for reception of laser communication signal, can we use it to efficiently couple the signal into single mode fiber? Very specific question. And what is the low power limit of these adaptive optic systems?
Maybe I'll start answering the first
Mm-hmm.
part of this. Absolutely, yes. Coupling. Once you have adaptive optic system, you get the diffraction limit. You can efficiently couple the light in single mode fiber. We actually already do this in astronomy because we have fiber spectrograph, fiber-fed spectrograph that use single mode fiber. So this is one of the key applications of adaptive optics in astronomy, is being able to couple light in single mode fibers. So the same thing applies to laser comm and any other field of using adaptive optics, the ability to go into single mode fiber. This actually connects to the other question, which is a photonic chip, which is a multi-channel version of single mode fibers with some coherent combining of the light. Again, adaptive optics enables us to not only inject in single mode fibers, but inject into photonic technologies. The low power level, I think it's hard to be quantitative, but this is really a question that's also linked to detectors. And detectors are getting very sensitive. Now we have detectors in both visible and infrared that can count photons at high speed. So I think the systems are getting quite sensitive. To be quantitative, we'd have to look at what is the requirement of the system, what is it looking at, and how much turbulence there is.
Mm-hmm. David, any comment from your side?
Again, I'm not so. This is very much more AO scientist and out of my remit. I'm much more of a RTC operator.
Olivier, I wanted to ask about because you mentioned that you can couple both into the single mode fire and then also into the PIC. Are the injection losses comparable?
Yes, they are. Coupling in a single mode fiber, the efficiency of the injection is is approximately equal to the Strel ratio. So that means in the infrared, in near infrared, we can get 60 to 80% of the light into a single mode fiber. On the photonic chip, this is similar because it's essentially multiple single mode fibers as the input. So I would say with extreme AO, we can get in the near infrared, we can get coupling efficiency between 60 and 80%.
Okay. I think the next question also comes into your photonic integrated circuits. Can you expand on the photonic integrated circuit subsystem you mentioned earlier and the maturity status of this project? I think you already mentioned it a couple of times.
Yeah, I will actually share my screen because I went very quickly on that slide, but it's worth just showing it again. So this is I just want to point out that the picture at the top is a real photonic chip, and the picture on the right is a real output on sky of a photonic chip. So the components of it, adaptive optics system is ahead of the photonic chip. The first part is coupling the light into single mode waveguides, and there are various ways to do this, but the way we've been doing this is there's a lens slat in front of each waveguide, and so light is coupled in a series of waveguide, and then it's injected into this chip that does the combination. And in the back end, we have an array of spots that come out. Some of them are dark because starlight has been canceled. Some of them are bright and are used for wavefront sensing. And then we spectrally disperse, and that's what you see in the image on the right. It's an actual on-sky image where you have multiple spectra. The wavelength is horizontal, and this is something that we've been running on sky at about a kilohertz acquisition frame rate, and we see this basically this spectra dancing gives us information about the wavefront, and you can see I find this very interesting, but most people maybe wouldn't notice, but some of those lines are missing. They're not missing, they're the ones where the photonic chip has been designed to cancel starlight. So if there is a planet, the spectra of the planet will show up in those seemingly missing lines, which are, to me, the most interesting ones.
It is. Another question comes to the turbulences. What is the time constant of the atmospheric disturbances that you are correcting, that you're trying to correct?
It's a few milliseconds. The time constant is a few milliseconds. It depends on the wavelength. It's longer in the infrared, shorter in the visible. for extreme adaptive optics because we're trying to do a very, very good correction. And we're looking at bright stars. We run our systems at a few kilohertz speed, so we can essentially go faster than the turbulence.
Mhm. David, I think next question is really for your part, because it's really on the deep already computational details. As far as I understand, the choice, that's question from Tommaso Furieri. As far
Mhm.
as I understand, the choice between using GPU or only CPUs depends on the system. If, for example, in case low check actuators numbers and slopes numbers, I guess that probably there is no gain in performance using a GPU for the command computation. In such case, do you still have advantage of using parallel computing in CPU, or is it better to have higher cache memory, or there are some other rules?
It's a very broad topic, but yeah. So in low actuator counts, you're probably not going to gain much on a standard NVM system going to GPUs because your I/O, because you have to transfer it from your network across into your GPU. But I think it's also again probably asking the wrong question for this. What is the skill of your team doing this? What's the skills of you? Unless you're going for something extreme AO like Olivier is presenting, your latencies are probably not going to be a problem on CPU or GPU. You're going to spend far more money building the system than you are purchasing hardware. So look at the skills of your team. If they're experts at CPU, use CPU. If they're expert GPU guys, use a GPU. I think unless you're building specific hard required systems, work to the strengths of your team. Yes, so for me, I prefer CPUs and abusing cache memory in CPUs. I find it easy in comparison to working with GPUs, but I know some of the teams working with GPUs these days find it far quicker and easier working with them. I would always put down to the skill set of your team over the choice of CPU or GPU. Both have come so far in the last 10 years that I don't think for small systems it matters.
So we don't need the latest NVIDIA, right, to run this system. Olivia, I think that's the question to you. Can the adaptive optics low power limit be circumvented with the help of laser guide stars?
Yes, absolutely. That's a great point, a great question. Astronomy, adaptive optics in astronomy has been very successfully using laser guide stars to look at places in the sky where there's no bright star. Uh, this is not, this is exactly what we don't have to face with extreme AO because we look at places where there is a bright star and we look for planets around it. So in extreme AO, we don't use laser guide star. But there's very exciting things going on in the laser guide star world where astronomers are using multiple laser guide stars to also get a volumetric understanding of the turbulence, which we could not do with natural guide star. There is also groups studying making a laser guide star from a satellite in orbit, shining at the telescope, and using this beacon to do adaptive optics, which would be quite amazing. The challenges are then a little bit more practical about the orbits. How do you align things and keep them aligned? But this the, this would be very exciting if we could get there.
Mhm. David, any comment from your side?
Yeah, not really to go much further, except for yeah, we are using laser guide stars for exactly that.
Mhm. Well, then there will be the last question. Are atmospheric wavefront errors typically compressible in some spatial mode basis? If so, would it be possible to reduce computational latency and memory requirements for wavefront sensing / reconstruction by exploiting compressibility?
I'll start by giving an interesting view on this, which is very specific to extreme adaptive optics. Uh, I think by and large, atmospheric turbulence in general is fairly chaotic and hard to compress. It tends to play out in ways that are hard to predict and cover all spatial frequency. However, in extreme adaptive optics, if we know where we're looking for a planet, if we know the region of the image where we're looking for a planet, we can focus our attention on the specific wavefront errors that would put light at that location. And in that case, yes, there are opportunities to do a better job by focusing on some spatial frequencies, some types of wavefront error, not because the atmosphere is only throwing those at us, but because those are the only ones we really care about fixing if we know where we're looking at the object.
Mhm. David, any comment? A closing
Yeah,
remark?
yeah. So I don't really have any knowledge of whether you can compress it down to some spatial modal basis, but there was a very interesting paper done by, well, part of a paper. It was a throwaway few paragraphs in the one by a guy called Ali Basden maybe 10, 15 years ago, where he reduced the bit um the number of bytes used in the RTC loop down from what you normally run. We're running at 32-bit floats down to, I think he found he got down to like 12 bytes of data per bit without actually losing any major performance. So you can gain huge amounts by using lower bit count in your matrices or looking at but I don't think there's been any long-term studies, or I'm not aware of them. Someone may have done it, but especially with the new GPUs coming out with the AI cores, tensor cores using mixed precision, yeah, there's ways of reducing your memory requirements looking at these. But I'm not sure if anyone's spent a lot of time working on it.
Well, thank you very much, gentlemen. It was a pleasure. I would like to cordially thank both of you for your presentations as well as the remarks. We had also very attentive and very inquiring public. So it was a pleasure. And thank you very much to the speakers, to the participants, and also to the ALPAO, our professional in the adaptive optics, who made this webinar possible. And on this positive remark, I'll close the session and once again congratulate everyone with International Day of Light. Let's keep looking in space. Bye bye, everyone.
Bye.
Bye.